is like the stack pointer always points to the last added data in the stack. Okay, so that's where the stack pointer points to, the last added data. And whenever you want to recover something from the stack, you always remove from the last memory location where the data was added. Okay, so what I mean is module 5 till if you are pushing, you have to pull the very last element that got added. Increment the stack, so you now point to the original. So you cannot pull this at the bottom. You have to remove them one by one. And this is called the top of the stack. Wherever you're storing stuffs, that's the stack top. Wherever you are recovering stuffs from the stack, that is also called the stack top. So you always push to the stack top, you always pull or pop from the stack top. And we saw what are the classifications. They have ascending stacks, descending stacks, and ARM has a descending stack. That's why the stack top is actually located at the bottom. Whenever you add new elements to the stack, it grows downwards. And whenever you pop elements from the stack, some space is, so it actually moves upwards, okay, when you remove something from the stack. The pointer move upwards or downwards. And which register controls this? Is the SP register R13. So stack pointer is decremented on push, incremented in pop. That's because ARM has a descending stack. Okay. Whenever you push something to the stack, right, the address gets decremented because now you're moving to a lower memory location. But whenever you pop something, actually, you are removing things, removing content from the stack, and you actually move upwards. Since you're moving upwards, it means you're moving to a higher memory address. That's why it's incremented on pop. And we saw that while pushing something to the stack, the order you define, it doesn't matter. Always, what happens? The lowest number registered is stored to the lowest memory address. So this is something that is followed. Similarly, when you pop, what happens? The lowest number gets popped first, right? So last in, first out. Whatever goes in last comes out first. So what went in last? The lowest number registered went in last. So the lowest number register would get popped first. Okay. And we saw illustrations, diagrammatic representations of how the stack gets filled with the register values, or how you can recover those registers from the stack. And we saw an example of a recursive procedure, right? So where we calculated the factorial of a given number. When n was less than 1, you return 1, but when n is greater than 1, you follow something like this. So this is, you can call this a nested procedure call, or to be more specific, a recursive procedure call, right? Because you're actually calling the same function from within the function, but with a different argument. Argument is decremented by 1. Okay. Every time you call the function, you call it using an argument decremented by 1. Okay, and how long do you call it? Until this condition is satisfied. So storing something to the stack is same as pushing something to the stack. Retrieving something from the stack is the same as popping something from the stack. So we have this push and pop instructions, right? If you want to push something to the stack, you make use of the push instruction. If you want to recover something or restore something from the stack, you make use of the pop instruction, right? And here we saw like an example. So that same example of the factorial function, but now we saw that using the memory map and the different registers that play a role, right? So what are the different registers that play a role while executing this piece of code? So we had a C code for calculating the factorial, and this is the equivalent assembly code for calculating the factorial. Okay. Now here you can see they make use of the push and pop instruction in order to store something from the stack and recover something from the stack. Why do we need to make use of these instructions here? Because a recursive procedure is also an example of a nested procedure, right? And in a nested procedure, the return address gets lost, so you want to store this LR to the stack. Okay. Now, why do you store this R4 to the stack? Because remember, we also store any value that we would need later. Okay. Or any value that could get garbled up. So that's why R4 is being stored to the stack. You have the program counter to keep track of the address of the next instruction. You have this LR for the return address. You have the stack pointer that points to the stack. Whenever you're adding new elements to the stack or removing new elements to the stack, this value gets updated. Okay, so we had a detailed discussion of how this proceeds. Okay, what happens, which instruction gets executed, which instruction is currently executing, which instruction would be executed next. So the green instruction is the one that's being currently executed, and the blue instruction is the one that gets executed next. And the program counter always stores the value of the next instruction to be executed. Okay, and due to the execution of this code, the stack pointer changes. Whenever you're making use of the push and pop instruction, the stack pointer changes, and the contents in the stack changes as well. Okay, whenever you have this BL calls, the value in the link register is updated, and it stores the address of the next instruction after the BL call. Okay, and based on some of this compare instructions, you get to know whether the branch will be taken or not, right? And the sub instruction and mul instruction actually modifies the value of this R4 and R0 register. R4 and R0, you have two registers, right? R4 and R0, you're making use of them. Here, R0 is an argument register, whereas R4 is a variable register. Okay. So you are never storing R0 to the stack, because you see within the push, you don't have R0. You are always storing R4 to the stack. So you're always storing a saved or a variable register to the stack. When do you store saved or variable registers to the stack? Whenever there's a chance that those values would get garbled up. Okay, so here R4 is a variable register, right? How did I know R4 is a variable register? From that pseudonym table. If you follow the pseudonym table, you would see that R4 is not an argument register, because R0 to R3 are argument registers. R4 is a variable register. And why you are pushing this R4 value to the stack? Because its values get garbled up. Okay, so you'd want to store that to the stack. And why do these values in R4 and R0 keep changing? They keep changing because of this sub instruction and this mul instruction. So you see the sub instruction, it decrements the value in R4 by 1 and stores that value in R0. Okay. And what does this mul do? Multiply those two values and store it in R0. So this R0 always keeps updating, and that is expected because R0 is a volatile register. Its value keeps changing spontaneously or frequently. Okay, so that's something that's expected of a volatile register.
So from this part, how can we expect a question?
So from this part, you might be asked, you might have a piece of code for a recursive function, let's say. So just an example, right? So probably it won't come up, but if you see a question, it could be something like an assembly code like this would be given, okay? And you could be asked to convert it to the C equivalent, right? So you can see this is the assembly code for the recursive function. But if you had to convert it to a C equivalent, it would just be those two pieces of lines, right? Which two pieces of lines? This or 3 lines.
Yes, sir.
Okay, this 3 lines. So this could be a one possibility. Other possibilities could be let's say I ask you what would be the value in the link register when a certain instruction gets executed. Okay, or how would the stack pointer change, the value in the stack pointer change, what would be the contents in the stack pointer. So whatever it would be simple, okay, nothing complicated. Now we understand why the value in this R0 changes. It is because you can see the sub S instruction updates the value in R0. The small instruction updates the value in R0. Why does the value in R4 change? Because this move instruction updates the value in R4. Okay, move R4 comma R0. Right, so that causes the changes in the value of those two registers. Right, so we saw how that code progressed and gave us the final output for the factorial of 3. Factorial of 3 is actually 6. That's how we obtain 6 through this piece of code. And here the new instructions that we learned were the push and pop instructions. Push instruction, you make use of the push instruction to store something to the stack. You make use of the pop instruction to restore those items from the stack. And you make use of through use of the pop instruction, you're basically incrementing your stack pointer and restoring the stack pointer to its original location before returning to the main function. That is necessary because the stack pointer always has to be restored before you move to the main function. So its value, the stack pointer value, is always guaranteed to be unchanged. Okay, that's why it must be restored before returning to the main function. Any questions regarding this module? So here, just the one example of a recursive function, right? Nothing more. Some basic facts regarding full descending stack. What does it mean? How are the registers pushed or popped from the stack? The structure it has, right? The data structure it has, the LIFO structure. Those are the topics that are covered in this module. So you want to revise all that. What else did we talk about? Module 8. So here, what are the data types? What's the size for each of those data types? Some different variants of the load and store instructions. And what are their equivalent C data types? So these are the equivalent C data types. And we had a structure like this, and the structure was used to form an array of 10 elements. And we saw how padding could be used to improve the speed, and without the padding, it's optimized for space. And we saw that without the padding, actually you would need more memory accesses to recover a particular word, and that is inefficient, right? So you would want to always, whenever you access the memory, you would want to read a useful word, right? But in this case, you can see there's a misalignment between the data. So that's why you don't actually read a complete word from one access. But you always want that. Whenever you're accessing the memory, you always want to read a useful word. By useful, I mean the word you need, okay? But here you can see part of the data is not aligned, okay? So that's why you have to make two memory address accesses in order to read the complete word. In order to avoid this type of a scenario, padding is used. So padding aligns the word, okay? So you are able to fetch the entire word using one memory access. And we compared these two pieces of code where in one, the x variable was declared as a local variable, in the other, the x variable was declared as a global variable. And we saw the effect of that on the assembly code and on the output that is produced, okay? Final output that is produced from the main function. What's important to note here is if you are declaring x as a local variable, it always gets initialized. So whenever there is a function called to foo, every time you have a function called to foo, your x variable is initialized because it has been declared as a local variable. But whenever you declare a variable as a global variable, it's only initialized once in the entire program lifetime. Okay, it's only initialized once, regardless of how many times you call the function. Okay, it's only initialized once. And this was from this slide, from slide 13, was basically we started talking about mixing C and assembly. Okay, here you can see that a function or a procedure has been written in assembly. What's the name of the procedure? Is strlen. strlen is a procedure written in assembly, and you wish to make use of this procedure using C code. Okay, how do you make use of this assembly procedure? By using this line, right, in your C code. You define the procedure using extern void. Why did you use the word extern? Because this strlen is an external function, because it hasn't been written in C, rather it has been written using assembly. Okay, so you define it as an external function. You use the word void to indicate that there's no explicit return from strlen. There is just implicit return, and within bracket you have a pointer to the string. Okay, the argument is a pointer to the string, and this is basically the syntax. This is the syntax. You have your data type, because a string is a char data type. You have the star mark, which is a pointer to the string, and then you have this s, which represents the string. So you're passing a string as an argument to the strlen function, and that strlen function calculates the length of the string for you and returns that to the C program. Okay, and within the assembly function, you should have something like this: export strlen. Okay, export keyword followed by the name of the function or the name of the procedure. So this line says that this line allows the export of this assembly function to the C function. So in order for the C program to make use of an assembly function, what do you have to do? You have to have these two lines. You have to define the assembly function from within the C program, and you have to have this line export strlen. So make the strlen function visible to your C program. Okay, you do that using the export keyword. Okay, make it visible to the C program. Also, you can access C variables, right? So you can see counter is a variable in C. If you want to access the value of this counter variable, or you want to read the value of this counter variable from an assembly program, how do you do that? You make use of this keyword import, right? Because now you want to read from a C function. Previously, you were allowing a C function to access an assembly function. Now you're accessing a C variable, which is why you use the import function, import keyword, followed by the name of the variable. Okay, so this way you are actually able to access a C variable or read the value stored in the variable. Okay, and this is actually a hybrid example where you can see these two lines, right? So these two lines, using these two lines, the external functions get value and set value are being used by the C program. Okay, you can see get value and set value are actually functions written in assembly. Okay, and you want to make use of those functions in your C program. That's why you have these two lines. You have to define them as external functions, and you can use them. Okay, also you have this lines export set value, right? Because you want to make this function visible to the C program. You have this export get value, because you want to make this get value function visible to the C program. You have this export increment. Just ignore this weak. Okay, so you have this export increment that makes the increment function visible to the C program. And why do you have this import counter? Because you want to read the value of the counter variable, and the counter variable is present within the C program. And here for increment, you don't see it defined as an external function, because this increment function is also a function within the C program, if you see at the bottom, right? So the increment function is already present in C as well. So this increment function has been written in both C, it's present in both C and assembly. So that's why it hasn't been declared as an external function. Okay, you can see within the main function, you're calling set value you're calling get value, you're calling increment. So set value and get value are actually external functions written in assembly. You can skip this slide, not included. Now, this slide talks about, so you saw example of C function, C program calling assembly function, but the vice versa could also happen. Right? So assembly can call a C function. That's possible. Right? So you have the same strlen function, but now it's written in C. Previously it was written in assembly, now it's written in C. Now, if you want to call this function, we know that a function is called using BL, right? The BL instruction, branch and link. Or you could simply make use of the B instruction, branch. So through BL, you're actually making a function call to a C function, strlen, right? But when you want to make use of this function, you also have to have this line within your C assembly program, that import strlen, okay? Because you want to import that. You want to make use of that C function. What's the difference? What's the difference between assembly calling C and C calling assembly? So this is a possible question, right? What's the difference?
export card लागते ना.
Okay, so when a C was calling assembly, remember that you had to define that assembly function as an external function.
External function.
Yeah, but here you don't have to define it as an external function. You just simply make use of the keyword import, right? That's the only thing you need to do. But there, while you were calling assembly from C, you actually had to define those assembly functions as external functions, and you also had to make use of the export keyword in order to make this assembly functions visible to the C program. Okay, so one you have import, the other you have export. One you have definition of an external function, and the other you don't. Okay, and whenever you want to access C variables, we discussed this, that whenever you want to access C variables from assembly, you have to make use of this keyword, import, right? So whenever you want to access anything, right, from C, you have to make use of the import keyword within your assembly program. Okay, and then finally here, you can see you are importing a bunch of stuffs, right? You're importing get value, you're importing increment, you're importing set value. What are these? These are all functions written in C, right? If you see the C program part on the right, get value, set value, and increment, they're all functions written in C. Okay, and if you want to make use of this functions written in C within your assembly program, you have to make use of the import keyword, right? This we already know. And if you want to make use of an assembly program within your C program, you have to define that assembly program as external, right? So here you see, it says this counter is an external function and the return type is an int type. Okay. Okay, so in this case, the counter is actually, so this is an example of accessing data defined in assembly. So this counter, what is this counter? You can see counter is at the very end here. So counter here is not a function. It's actually a data. Okay. So if you see the header of this slide, it says accessing data defined in assembly. So counter is actually a data defined in assembly. If you see the bottom last, second last line, towards the bottom within the assembly code, this is the line. This line, using this line, you're defining a data, okay, in assembly. And if you want to access the data, you have to have this line in your C program. Okay, you have to declare that using this keyword's extern, which says this is an external data. It comes from the assembly program, and int says it's int type. Okay, this data. What change do you have to bring within the assembly program? You should have something like export counter, so that this counter variable is actually visible to the C program. Okay, so this is something we already know.
Sir, what's the function of the DCD?
So this is through this line you're actually defining a data. Okay, so you know that it's possible that the data doesn't have a single value. It could be a structure, it could be a heap. Okay, so there are other complex forms of data, right? So this is not really important how the data is defined, but the point is whenever you have a data being defined, this is how you can access it. So right, it could be any other data or any other variable. That's fine. So here it doesn't really give a lot of context. Okay, from this context, it's not possible to understand what is this DCD. But what we know is it's a piece of data. Okay, that's been declared within the assembly program, and the C program wants to access the data. And that's an external data, so you have this external keyword. And right, we know why to use export. We know what this BL does. We know why to use this import. Okay. So this is an example of mixed CN assembly. So here on the left, you can actually see something like a C function, right? So my func, this kind of looks like a C function because you don't have any assembly instructions there. Then you have this extern int counter. What does this mean? So counter here, counter is, it says it's an external data. Okay, and it's int type. External data that is int type, and it's written in assembly. Okay, or it's defined in assembly, which is why you have this extern. Now, why do we call this mixed C and assembly? If you see the portion on the right, you see it starts like a C function. The sum is, it kind of looks like a C function, right? Because in assembly you would have this starting with the label sum followed by the colon, and then you have an instruction. But here, you see it's been defined like a C function, right? But within the brackets, you see it has been defined using assembly. It started with like a C function, but within the brackets, the commands that have been used were defined using assembly. Whenever you do something like this, you have to make use of this underscore ASM, okay? Because you are doing something, you're trying to do something hybrid. You're trying to form a piece of hybrid code, okay? So you need to make use of this underscore ASM. And if you look inside the function, it's all in assembly, right? You can see the use of this push instruction, add instruction, branch instruction, branch and link instruction, pop instruction, BXLR. So all of that are assembly instructions, right? So the entire thing within has been defined using assembly, but it started like a C function. Okay, so you can see the counter is actually, it has this dot word or dot data. So this is actually a piece of data. It's not a function. Okay, and we already know how to access data defined from the previous slide. Excuse me. Okay, any questions regarding this module? You guys can hear me, right?
Yes, sir.
Yes, sir. No, sir, no question.
Right, so this external int counter, it comes from this last line, the same external int counter. But here counter was defined differently, right? It was DCD0, but here you see a different definition for counter. How it has been defined doesn't matter. Just remember that counter is just a piece of data. Okay, and whenever a data has been defined in assembly and you want to make use of that data in C, you have to have this line, extern followed by the data type followed by the name of the defined data.
So should we remember the conversion with the will it come like a multiple choice?
I mean, it could come like a multiple choice or true false statement or short theory question.
Okay, thank you.
All right. So recently, yeah, any
স্যার
question?
মেইনলি অনেকগুলি কোশ্চেনের টাইপই এরকমই থাকবে, কনসেপচুয়াল, তাই তো?
Yeah, it would be mostly conceptual. Correct. So here, this counter, right? So this counter thing, you can consider this to be a data variable. Okay, that's perfectly fine to consider this to be a data variable. Here it has a complex data structure, but it could be something simple as well. Okay, something simple, and you would still make use of it the same way using this line. Yes, Shradul, do you have a question? Right, so let's hop on to the last modules, which are GPIO. We have been talking about this recently. Two ways you can interface with GPIO: port mapped and memory mapped. So port map is kind of inconvenient, so we mostly use memory mapped. Okay. For port map, you need special CPU instructions, but for memory mapped, you can just use the load and store instructions we already saw. This is more simpler, more convenient. And here, each register is assigned to the address space. Okay, you can see one of the registers is assigned to this address, right? So using the store instruction, okay, using the store instruction, you can actually assign registers to memory spaces. That's what is like memory mapped IO. This is more convenient, and this is what is most commonly used. Okay, in ARM probably this is the only option you have, memory mapped. Okay, in ARM you have to make use of memory mapped IO in order for your input output devices to interact or communicate with your CPU or core. Okay, your core interacts with the input output devices using memory mapped IO. It's a protocol to interface with the peripherals. Here it just says what the sections are for, what's the use of each section. Okay, we're mostly concerned in this chapter about this peripheral section, and you can see it has information about the different buses, HB and APB, the high performance and the peripheral bus, and the peripherals such as GPIO, timer, SPI, UART, stuff like that. This section has information about all that. The types of buses, high performance for the high speed, high performing, high bandwidth components, and APB for the slower components or the low bandwidth components. You have 8 different ports for GPIO, and each port can contain up to 16 pins. Okay, and those pins are actually used to interact with your input or output devices. Okay. So here you can see the GPIO is actually connected to AHB, the high performance bus, whereas the slower components such as UART, SPI, and timer are connected to the APB bus. And to the AHB bus, you can see your processor and flash SRAM connected because they are like high performing components, your processor, as well as the memory devices, memory components like caches. Then the 12 registers, each port has 12 registers. So although you can see that 1 kilobyte is assigned for each port, only the registers only take up 48 bytes, right? Because each register is 4 byte, 12 registers are 48 bytes. How can you set pin 14 of port A to high? Using the ODR register, you can set pin 14 of port A to be high. Now we discussed what was the little endian configuration. According to the little endian configuration, so this at the bottom you can see is 32 bits for the ODR register. Okay, at the bottom you can see the 32 bits for the ODR register. Now if the top byte, okay, or the topmost 8 bits enter the highest memory location and the bottom byte enters the lowest memory location, this kind of a configuration is called the little endian configuration. Okay, and vice versa is called big endian. What's big endian? Big endian is if the bottom byte entered the top memory location, which is this memory location. Okay, 17 at the end of that address. Any confusion regarding little endian and big endian? It's pretty clear from the diagram.
আবার একটু রিপিট করবেন কি?
Yeah, so you can see at the bottom you have 32 bits of the ODR register. Right? You have 32 bits of the ODR register represented at the bottom. Now, if the bottom 8 bits or the bottom byte enters the lowest memory address. Here, what's the lowest memory address? So this is your total memory address, right? 14, 15, 16, 17. So the lowest memory address is 14. So if the bottom byte enters the lowest memory address and the top byte enters the highest memory address, you call it the little endian configuration. Now, if this bottom byte entered the top memory location, highest memory location, which is 17, and this top byte entered the lowest memory location, which is 14, you would call it the big endian configuration. Is this part clear?
ওকে স্যার, ক্লিয়ার।
You could also read the notes here, okay, in order to revise. Now, how you set that pin 14 value to 1 is using this statement. Okay, using this statement, you can set the value at pin 14 to 1. So you can see this is your bit 14. How can you set this to 1? Using this expression, you can see here you have this number 14 and you're saying perform a bitwise OR with the number 1 on bit 14. So if you do a bitwise OR with 1 on bit 14, whatever the value was previously in bit 14, it would get updated to 1. Okay, and how does it come to this location? Is because you're using this address. Okay, you're using the address which marks the start of the ODR register. So the starting address of this ODR register is this address. So you are using that address. Okay, right, so you're using a pointer to that address, or you're storing that address in a variable, in a 32-bit unsigned integer variable. You're storing that address. That address is a starting address of your ODR register. Okay, that's how it goes to that location, fetches that value, and performs a bitwise OR on the 14th bit using 1. Okay, bitwise OR with the value 1 on the 14th bit. This is an example of dereferencing a pointer. Why is it called dereferencing a pointer? Because you're pointing to a specific memory address and you are fetching the value, or reading the value from that memory address. This is an example of dereferencing a pointer. It's a term, it's a computer science term, okay, of reading from a particular memory location. But this kind of a definition is inconvenient because it makes use of an address. An address can be difficult to write, right? So it's not very good for the code readability. Okay, the readability reduces if you have addresses. So it's always better to replace those addresses with variables, which is what we do in the next slide. We have a different variable for the different registers, and each variable actually stores the value in the register. And all of these are unsigned 32-bit integer variables. You're declaring them as volatile, indicating that their values keep changing frequently. And it asks the operating system not to do that optimization. Which optimization? Usually the operating system does an optimization. Instead of continuously accessing the memory, it reads from these variables and it doesn't access the memory. Okay, it reduces the number of memory accesses and it reads from the variables whenever an optimization is done. But whenever you declare something like using this volatile keyword, you tell to the operating system that don't go for such type of an optimization. Okay? And the values in these variables keep changing frequently. That's why the volatile keyword is there. And how do you achieve something like this? How do you make the 14-bit high? Using this is through this expression. So things become simple. Now you can see in the expression, you don't have an address, you just have the name of a variable, right? So you go to port A. So you go to this port A, you select this variable ODR, right? And the 14th bit, in the 14th bit, you do this OR operation with the number 1, so it turns high. And here we discussed how we could light up this LED. Right, this LED is an output device that is connected to pin 2 of port B. And we want to turn this on. In order to turn that on, we have to have the value 1 at the pin PB2. How can we make that value 1? Is using the ODR register rate. So the ODR register controls the value at the pin. Okay. Now, a pin can have 4 different functionalities. It could either be in the input mode, it could be an input pin, it could be an output pin, it could have an alternate function, or it could have an analog function. Okay. So a pin can have 4 different modes. So in order to turn on this LED, we would want our pin to be in the output mode. Right? When do we want our pin to be in the input mode? So whenever it's connected to an input. But here it's connected to an output device, so we want it to be an output. And how do we make this the output? Is through the mode R register. This mode register controls the functionality of the pins. Okay, so for this example, we want the pin to be in the output mode. So that's why. And which pin are we talking about? We're talking about pin 2. Right? So you can see the mode register actually has 32 bits, and 2 bits are reserved for each pin, because you need 2 bits to represent the 4 different modes. We're talking about pin 2, so we're concerned about bits 4 and 5. And this bits 4 and 5 should be actually 0, 1, because 0, 1 represents the output mode. How do we make it 0, 1? Using these 2 pieces of line. Okay, and we're talking about port B, because the pin name is PB2. We're talking about port B. Go to port B, use the mode R register, and on bit 4, whenever you write 4 here, it takes into account 4 and 5, because 4 and 5 are part of pin 2. It doesn't take into account 3, because 3 is part of a different pin. Okay, whenever you write 4, it considers bits 4 and 5, and it does a bitwise AND on bit 4 and 5 with not of 3. So 3 means 1, 1, not of 3, 0, 0. It does a bitwise AND with 0, 0. Okay, whatever the values are for bits 4 and 5. And if you know that if you do bitwise AND with 0, 0, whatever the values were, they would become 0, 0. Right, so this is how, using the first line, you cleared the bits 4 and 5. And after that, you want to make it something similar to this 0, 1. Right? You don't want it to be 0, 0, you want it to be 0, 1, because 0, 1 represents the output mode. How do you make it 0, 1? From there, using the next line, using this line. What you're doing, you're taking the 4th bit, and using that 4th bit, on that 4th bit, you perform a bitwise OR with 1. Okay, so 0 or 1 becomes 1. So 4th bit becomes 1, and now you have 0 in 5, 1 in 4, 0, 1 represents the output mode. That's how you can convert to the output mode. So now your pin becomes an output pin, and using ODR, you can select the value to be 1. Right, you can make the output high in order to turn on the LED. Something else you have to do is you have to define the output type, and that's done using the O type register. It defines the output type. Output type can either be push-pull or open drain. We always want it to be push-pull because of reasons we saw in the last module. Why we always want it to be in the push-pull state is because push-pull always gives you a valid output. Okay. But open drain has a problem with one of the scenarios. It doesn't always give you, it sometimes produces a high impedance value. Okay, but that's not the case with push-pull. It always gives you a valid value. So that's why we always use push-pull. Okay, so you would want to define the output type as push-pull. And if you see the internals of this register, the first 16 are reserved. The next 16 is for the pins. 16 pins and 16 bits are reserved. So 1 bit for each pin. 1 bit is enough. because you just have these two states, 0 and 1. So 1 bit is enough to represent them. And you would want to make this second bit 2 0. Why do you want to make bit 2 0? Because bit 2 represents pin 2, and we are talking about the pin PB2 here. The pin PB2 is connected to the LED. So we are concerned about bit 2, and we want to make this 0, right? So that the output becomes push-pull type. How do we make it 0? By this line. It says go to port B, select the O-type register, perform a bitwise AND on bit 2, perform a bitwise AND with not 1. Not 1 means 0. So whatever the value is there in bit 2, that gets ANDed with 0. ANDing anything with 0 produces a 0. So you get a value of 0, and 0 means it's in the output type is actually push-pull. Right? So these are the 3 registers you need. In the last module, you saw that there's one more register you need. That's the PUPDR register, pull up, pull down register. And it actually defines what type of register you're connecting internally your pin with, right? Is it a pull up or is it a pull down? So internally, why do you need to connect it with a resistor? So for this case, this input pin might have 3 different states, right? A high or a low or a high impedance. So that a high impedance value doesn't appear at this input internally, you make use of either a push pull up or a pull down register. Okay, because you always want a valid value at this input internally. Okay. If you don't have this pull up or pull down register, what happens? If this input pin had a high impedance value, you would also see a high impedance value internally. So if you had a high impedance value at this pin, you would see a high impedance value internally here if you didn't have this pull up resistor. Okay. Same as this. If you had a high impedance value here at the pin, you would see a high impedance value here internally if you didn't have this pull down resistor. So in order to avoid that kind of a scenario, so that even if we have a high impedance value at the pin, it either gets pulled up to a valid high or it gets pulled down to a valid low, we make use of a pull up or a pull down resistor. Okay. And this slide repeats the same thing, that you could have either of these 3 states at the pin, and you use a pull up or pull down to ensure that you get a valid input internally, be it either logic 1 or logic 0. You'll get a logic 1 if you're using a pull up register, you'll get a logic 0 if you're using a pull down register. So you only need them when the external circuit does not drive the pin. That means what? The external circuit produces a high impedance value at the pin. Okay, when it's configured as pull down, what happens? The pin is internally connected to the ground through a resistor. When it's pull up, it's internally connected to the power supply through a resistor. When it's neither pulled up or pulled down, the pin has a high impedance value. That means what? A high impedance value appears internally. Okay. So this pin is connected to an external circuit, and that external circuit might sometimes produce a faulty value or a high impedance value. But you don't want that high impedance value to appear internally within your processor chip. Now this registers, pull up and the pull down registers, they have a very high impedance, usually in the range of 10 kilo ohms. So in order to pull up the high impedance value to 1 or pull down the high impedance value to 0, it takes a lot of time. Okay, because this resistors current, only a small amount of current flows through this resistor. So the pulling up or the pulling down action takes a long time. Okay, so what would you want if, in order to overcome the situation, you have this external circuit, and in this external circuit, you want a similar pull up or a pull down network, but this time using low impedance, okay, or low Z values. So that helps to overcome this problem. Okay, if you have an external circuit, that's what this says, that the internal pull up and the pull down resistors have large impedance, larger than 10 kilo ohms. And when external circuit connected to this pin has a fair amount of capacitance, the process of pulling up, pulling the pin voltage to logic high or logic low takes a long time. Okay, this is because of the impedance of the internal pull up and pull down resistor is so large. So in order to meet the speed requirements, you need external pull up or pull down with small registers. Okay, you have that external circuit and you would want to have external pull up or pull down there with small resistors. Right, we saw that push pull always gives you a valid output. Whenever here you have 1, in the pin you have 1 as well, because this becomes open, this becomes closed. So this is off, this is on, and a current flows from this VCC to the pin, making it high. Okay, so this you have 1 here and 1 here as well. So the bit value is preserved, you get a valid output. And same thing happens like whenever you have 0 here, this becomes off, this becomes on. So here you see a closed switch, current flows through the switch to the ground, and at the output you see a 0. Okay, so the bit value is maintained, you get a valid and you get the same value at the pin. So that's why we always go for push pull. But for open drain, here you see you have a 0 here, and the output you get a 0 as well. That's fine, but that's not the case if you had a 1 here. Because if you had a 1 here, this would turn off. Okay, and there's no pull-up network that would take this to 1. Okay, so you see a high impedance value at the output, but that's shown in the next slide. Guys, do you think you need a break?
So 5 minutes.
Yeah, that's fine. So 5 minutes break and then we would come back. Module 5 till module 10. That includes the conversions from assembly instruction to machine code. So since you didn't have any such conversion in the midterm, you can expect to see such conversions in the final. Then we talked about procedures, we talked about stack recursion, and finally we concluded with GPIOs. So if you have any problem regarding any particular topic, we can go through that first. If anyone doesn't have a problem, like a specific topic or something, then we would just do a general review, can kind of discuss what could come up chapters. So from this you should see some questions in the final. Now, as you've seen in the mid, there were questions from almost all aspects, right? So there's nothing that we could really skip. There were questions from barrel shifter, addressing modes, what else? Hardware components, flags, right? So everything is kind of important. So from this chapter, we started talking about instructions and that they could be represented as data. So because instructions could be represented as data, it made it possible for us to use the same memory technology for both, right? So same memory technology as in caches. So you use caches to store data or numbers. Similarly, you can use caches to store instructions, because instructions are nothing but a series of numbers like data. Everything has a memory address, and so branches make use of memory address, as we know. In order to jump to a particular label or a target, it needs an address, right? So every target or label has a unique address, and branches make use of that in order to jump to those addresses. Here a question, I think it was true false, right? So C pointers, memory addresses, also the significance of program counter and instruction register. You had that in your midterm. Probably the things that already came up in the midterm won't be there in the finals, okay? So you had questions related to the hardware components of ARM. Of course, that's not part of this final syllabus. And you saw questions regarding flags, program counter, instruction register, RISC and CISC, the architectures, um, constant multiplication, constant division, addressing modes, barrel shifter, branches, right? And then a coding problem. So the final would be kind of similar. Make sure that you revise the slides well. You don't skip anything from the slides. Okay, and you might expect some MCQs and true false like the midterm. So be mostly focused on the theory. And machines are backward compatible, meaning that they want to run the older programs. They want the older instructions to execute in the latest PCs as well. So instruction sets evolve over time, right? Because you have more and more instructions being added to the instruction set. Why is that? That's because you now want to achieve more. Okay, you want to do more complex tasks. So that's why you need new instructions. So the instruction set keeps evolving over time. I think you had a question in the midterm regarding thumb instructions. Okay, so all of this we saw the conversion from instruction to machine code. All of that will be there. So you could expect some questions from here, and you'd be given the necessary data. So you'll be basically given the ARM reference card. Okay, so the ARM reference card looks like this. So you would have this table, or this opcodes, this fields, all of this. Okay.
सर स्लाइड 3 टेक तो मुझे ओके सॉरी
Yeah, what's that again?
सर आर्म कार्ड इंस्ट्रक्शन जेटे कैसे सर स्लाइड 3 का सर
Okay, slide 3. Okay. Yes.
सर ये যেখানে যে স্যার আপনার 4 নাম্বার বিটটা স্যার একবার 1 থাকতেছে সামটাইমস এন্ড সামটাইমস देयर আর 0 স্যার এই রিজনটা স্যার
Okay, so there are two ways that you can apply this shift, right? You can see a shift field. So you can apply a shift to this register RM, right?
यस सर
To the value in RM. Now you can apply this shift in two ways. You can either apply the shift manually. That's when you have this left configuration, the one in the left. You can see that bits 7 to 11. Right? These
Yes,
bits
sir.
are how many bits are there? 7, 8, 9, 10, 11. So 5 bits. So this is a 5-bit unsigned integer that you can use to use as the shift amount to apply shift on the value in this register RM. Okay, so this you use on the left. This is the one you use when you have to when you manually apply the shift. But on the right, you use this whenever you don't want to manually apply the shift, but you use another register RS to apply the shift. So RS is another register. It's called the shift register. It could be just excuse me for a minute, okay? Yeah, sorry for the interruption. We're discussing. Can you hear me?
Yes, sir.
Okay, so we were discussing this slide. So this on the left is to manually apply the shift, and on the right you make use of another register to apply the shift. You take the shift register, and it has 32 bits, but we only use the bottom byte. So that means the last 8 bits. So you whatever the value is in the last 8 bits, that value is used as the shift. Okay, so that is manually. So that is making use of a register to apply the shift instead of writing the shift directly. Okay.
Yes, sir.
Applying the shift directly, and you would have this thing given. This is for the condition field. Yeah. Yeah. So whatever you see here would be given. Okay, it would be exactly the same as the 6 slides. Okay, this one is not there in the ARM reference card, but let's say if I can include this, if I can include this, I think that would be better. But if I don't include this, probably there won't be any questions related to this. Okay, so this is just making use of the pseudonyms. And we know that there's only a limited space that is assigned for the constants, right? Because the entire number or an entire instruction is 32 bits. Okay, and only 8 bits are reserved for the constant. So in order to extend it, we need barrel shifters. And we discussed the use of barrel shifter and the significance of barrel shifter. And we saw the shifts and rotates. So this, excuse me. Distractions today. Okay, so the shifts and rotates. Right, so this was covered in detail in module 4. Here you just need them for some of the instructions, right? So some of the instructions might have LSL, LSR, ASR, or ROR. So that's why you have this slide. And we discussed different examples for data processing instructions. All of that is important. You will want to revise that. Any problem understanding any of the instructions that we discussed, any of the examples? Then we talked about branch instructions. Right, how we make use of this formula. How the offset helps us jump instructions, how many instructions it can jump, how many words, how many bytes it can jump, and the conversion from word to bytes whenever we make use of this equation. Right, we saw all that. So this we updated. So when we don't take the branch, this is how the program counter is updated. I hope you can hear me. So if we don't take the branch, this is how we update or increment the program counter. It's just PC equal to PC plus 4, where you just move or you just execute the next instruction, okay, the immediate next instruction. But whenever we take the branch, we add this term, offset times 4. Why are we doing offset times 4? Because offset is in terms of words. We multiply that 4, but we multiply the offset by 4 in order to convert it to bytes. Okay, and we know that we need to make this conversion from word to bytes so that we can make use of this entire equation, right? Because memory address is always in terms of bytes. Okay, so you would want to convert the offset from words to bytes and then add it with PC plus 8. Why PC plus 8 and why not PC? We discussed that it is because of pipelining, right? It is because of the hardware. Whenever you're executing a particular instruction, actually the next instruction is being fetched. Okay, so I think we could go over that again in short. So there are different stages in a pipeline. First is the instruction fetch, instruction decode, and execution. So let's say we are executing instruction 1. That means instruction 2 is in the decode stage. We are assuming that they are simple RISC instructions that take one cycle to execute, or one cycle to process. Okay, so instruction 2 is in decode stage and instruction 3 is in the fetch state. So whenever you're executing instruction 1, actually the third instruction is in the fetch state. So that's where PC plus 8 comes into the picture. If this instruction 1 has an address of PC, instruction 3 would have an address of PC plus 8, and we add the offset with this PC plus 8, right? Because that's the instruction that's been fetched. That's the last instruction in the pipeline. Okay, so instruction 3 has an address of PC plus 8, and the offset is calculated with respect to the instruction that has been fetched. So why is this necessary? We always want the pipeline to be full in order to maximize the instruction throughput and reduce any pipeline stalls. Okay, so this is done to maximize the efficiency of the system so that we get enhanced throughput. So that's why. Okay, any confusion regarding this? Why we add the offset to PC plus 8 and not PC? If you want a detailed understanding or a better understanding, you could always refer to this document. It has all of that in detail. Okay, here so you can go through this, but that's the basic idea, that we add the offset to PC plus 8 due to pipelining, and this helps maximize instruction throughput and reduce pipeline stalls. So this bullet is kind of important. By using PC plus 8, the processor is fetching the instruction that comes after the next instruction in memory, effectively assuming that the branch is taken. This helps keep the pipeline filled with instructions even if the branch instruction turns out to be taken. Okay, any questions regarding this? Why we add this to PC plus 8 and not PC? So it comes from this concept that whenever you're executing instruction 1, your instruction 3 is in the fetch state, and your program counter actually stores PC plus 8. Okay, whenever you're executing instruction 1. So that's why this offset is in terms of PC, and PC is actually PC plus 8. Okay, whenever instruction 1 is being executed. Now we looked at some examples involving branch instructions. So this could come up in the exam. So I haven't really started preparing the question yet. I will do that soon. but it would cover these things. So nothing out of the syllabus. Everything would be there from the slides. And what we use if else for branches for? We use them to implement if else statements and loops. So whenever you have a loop, you would want to convert that to if else statements and then implement those if else statements using branches. And how to handle cases if the offset is too large. You would want to answer these 3 questions, practice these 3 questions. Finally, we talked about data transfer instructions, which involves loads and stores, right? We talked about the addressing modes. We discussed a few examples related to loads and stores, and that was it for this chapter. Okay, any questions from this module?
So data transfer module পার্টটুকু থেকে কি দেখা লাগবে?
One more time.
ডেটা ট্রান্সফার পার্টটুকু থেকে কি দেখা লাগবে?
Data transfer, you would want to know how you would fill up these fields, all those different fields, right? Offset, destination register, base register, condition fields, intermediate, pre or post indexing. Then if it's a byte transfer, if it's a load, if it's a write back, if you're adding the offset or subtracting the offset. So you'd want to know how to fill up these fields. If you're given an instruction, either a load instruction or a store instruction, you would want to know how to convert it to machine code. Okay, so that's one thing. Also, you might be asked about the addressing modes. Also, you might be given something like a memory map where you have several memory locations, and you might be asked where does data go, or from which location do you read, stuff like that. Okay.
Okay.
Or you might be given something. So you've seen how a memory map looks like, right? So let me just show you here. So something like this, right? So this, let's say you have several memory locations, and based on some given information, you might be asked to fill up the space with data, or you might see some data here and you might be asked like what would be the output. Okay, something like that.
Oh.
If you saw the video on addressing modes, you saw like something like this, right? If you saw the video on addressing modes, they have something like this, different memory locations, and that's filled up with data. So how to work with those, okay, data and memory locations. Right, any other questions from module 5? If not, let's move to module 6. So here we talked about procedures and the standard convention. So we would always want to follow the standard convention. What was the standard convention? You make use of R0 to R3. So this R0 to R3, their pseudonyms are in terms of A, okay? So this registers, their pseudonyms are in terms of A. So they're called A1 to A4, I think. Yeah, A1 to A4. Okay. So this registers are called A1 to A4. Those are the pseudonyms, and A stands for argument. So this registers are basically used to pass on arguments and pass on the output. Okay, return output. So you would want to make use of this registers when passing on arguments and the return output. Similarly, the ones you see next, R4 to R11, their pseudonyms are in terms of V. V stands for the variable registers. They're called the variable registers because they hold the value of the local or global variables. Okay. So whenever you're dealing with variables, you would want to make use of this registers to store those variables. So we saw an example. What was the example? In the example, we had a main function. Okay, and the main function was calling another subfunction, the subroutine sum. So this is the subroutine that you see. And then we try to implement this using assembly. Right? So this is how we try to implement it using assembly. So you see the conversion from C to assembly. And we saw the use of BL and BX instructions. Okay, so BL is whenever you want to jump to a particular label or target, as well, you want to update the value of the link register so that you can return to the link afterwards. Okay. So, or what you could do is manually move the address to the link register and then do a simple branch B instead of BL. You could do a simple branch to the label. And then after you're done executing that subroutine, you return using BXLR, you return to this address 1016. Okay, so that's the immediate next instruction after the branch instruction. Any question regarding this concept of BX? I think you saw this during your labs as well. So why you use BX here is to return to somewhere in the code, right? Return to some place in the code as indicated by the value in this LR register. Okay, so these are two alternate ways. You can manually update the address in the link register, or you can make use of the BL instruction. So BL instruction automatically updates the address in the link register. So this BL instruction has two functions, right? It helps you branch to a particular label, and it updates your link register to store the address of the next instruction. And this is the syntax for BX. BX is always followed by a register. It's never followed by a label. So BL stores the return address in the link register, and this BXLR jumps back to that address in the link register. We saw an example of a nested procedure where this sum square function was actually calling another function mult from within. So this is an example of a nested procedure, and we discussed that in a nested procedure, the return address for sum square is actually lost. So the sum square would want to return an output to the main function because the main function would be calling the sum function, or some other function could be calling the sum function as well, right? So whichever function calls the sum square function, it has to return an output to that caller function. But it is not, whenever this kind of a nested procedure is there, or a nested function call is there, the return address is actually lost. So you would want to store that return address somewhere before making the nested procedure call. Okay, so that's the summary of this. And we saw the type of regions there are within the SRAM. Okay, what are the regions within SRAM? You have a space for stack, space called stack. You have heap. You have a space for the static variables, which are the global variables. So those are the different sections you see, exactly like this. So you have a space reserved for local variables and procedure calls. That's called the stack. For global variables, you have a space assigned. That's, you can see it has been denoted by the term static. The space is reserved for the static variables, and you have the heap for the variables whose size change during runtime. So for dynamic variables. Okay, and at the bottom you have this code. So this is actually not part of the SRAM. This is your instruction cache, or you could call it flash memory. Your flash. This is for the program. So whenever you have to deal with nested procedures, you extensively make use of the stack. Okay, because you would want to store the return address to the stack because it gets lost whenever you're calling another function, right? You're calling a nested function. So you use the stack pointer, you increment the stack pointer to create some space on the stack. Why do you increment it? Because why do you increment and not decrement it? Because whenever you increment it, you're creating space, because this is ARM has a descending stack, right? ARM has a descending stack, which is why you do something like this to create space on the stack. And see, using this line, you're actually storing the return address. Okay, because you know the return address will get lost whenever you're doing this BL mult. This BL mult is this is used to call the mult function. The mult function, as you saw, was a nested function, right? So whenever you do something like BL mult, you're calling the nested function. Your return address is lost, so you would want to store the return address, your stack, and you would want to store any variable that you need later, right? So in this case, if you see, you need this variable y. So whatever output is produced by the mult function, that output is added to this variable y. So besides storing the return address in the stack, you would want to store the value of y in the stack as well. So that is being achieved by the third line. So this third line, it stores y in the stack. And after you do the function call, you move to this label, mult. Mult does this operation. Then you have this bxlr, and you return to the next address after the BL call. Okay, so you return to this LDR. After you return to the LDR, so what are you doing through this instruction? You restore y. So you saved y to your stack. Now you restore your y. Okay, because now you need that y for the calculation. You restore y in register R1. Okay, and you add that value to whatever was the output from the mult function, and you then get the final result, R0. This is the result for the sum square function. Okay, so now this R0 will be returned to the main function, because if assuming that the main function was calling the sum square function. And also you can see that the return address is being loaded to the link register using this instruction. This line is incrementing your stack pointer. So this basically restores your stack to the original place. Okay, we know that we have to always restore the stack to its original place before leaving the function. So after we are done restoring the stack to its original position, we then have this bxlr, through which we move to the main function. Okay, that was calling sum square. So this kind of the first part is the push. We saw what are push and pop instructions. So the first part represents push. It's the backend code for a push, and then you have this pop. So what's push? Whenever you push something to your stack, right? That's a push. Whenever you retrieve something from the stack, that's a pop. Whenever you store something on the stack, that's a push. Whenever you retrieve something from the stack, that's a pop. Okay. So any questions regarding any of the lines here in the slide? So this kind of gives you the steps, right, that you need to follow while making a procedure call. You save the necessary values to the stack. Any arguments that you need to pass on, you need to assign those arguments to certain variables. So you make use of the argument registers here, A1 to A4. Okay, you make the BL call. Then you restore values from the stack. You restore the stack pointer, and then you finally use bxlr to return to the main function. Okay. There are some rules you need to follow. Rules as in the standard conventions. So we have already discussed that, standard conventions. And so this bullet is kind of important. It says, whenever callee returns from executing, the caller needs to know which registers may have changed and which are guaranteed to be unchanged. So there are some things that are guaranteed to be unchanged, right? Whenever a callee returns from executing, what are the things that are unchanged? What are the things that are guaranteed to be unchanged? So the stack pointer is guaranteed to be unchanged, right? Because you always restore the stack pointer before making the function call. So the stack pointer is always guaranteed to be unchanged. What else is guaranteed to be unchanged? The variable registers are guaranteed to be unchanged because you see, you always have to restore them if you change them. However, these things are not guaranteed to be unchanged because they can change. So every time you make a BL call, the LR register is updated, right? So they can change. The argument registers are called the volatile registers. So volatile means their values keep changing frequently. So argument registers can change as well. So they are not guaranteed to be unchanged. Okay. Right, so for the variable registers, if there is any chance that the callee function would garble up the values in the variable register, you would always want to store these values in the variable registers to the stack. And then before returning, you would want to restore those values from the stack so that these variable registers contain the original ungarbled up values. Okay, so remember we discussed this. Similarly, for this argument registers, if you would need these values later, you would want to store them to the stack. Okay. For example, in the previous example we discussed here, we saved the value of y, right? We saved the value of y to the stack. Why did we save the value? Because we would need that later, right? So for this intermediate calculation. So save any temporary registers before making the function call, and you save any save registers before garbling up their values. Okay, so why do you need to store the values in the temporary registers? If you need them later, you need to store them to the stack. For the save registers, if you think they would get garbled up, you would want to save them to the stack. Okay, and only the ones that are being used, they need to be stored to the stack. Not all the registers need to be stored to the stack. So this is kind of a general summary of what we already discussed, that this is how you decrement the stack pointer and create some space in the stack. After you have some space in the stack, now you are good to store different things in the stack. Okay, you can store the return address. If it's a nested procedure call, you need to store the return address because it is lost whenever calling a nested function. Also, you might need to save other registers if you're needing their values later, or if the values could get garbled up. Right. So once you're done with the nested function call, you restore the values from the stack. Okay, you restore any variables that you saved. You restore the return address that you saved, and then finally you increment your stack pointer so that your stack pointer points to the original location. Okay, and then you do this VXLR to return to the main function, or whichever function is calling the function. Then we saw this code conversion. This was simple. First part was a main function which was calling the same function but using different arguments. Okay, and you're storing the result in different variables as well. A mapping was given. Right, we converted that to assembly. So here you can see the main function is calling the mult function, and the mult function looks like this at the bottom. It has two arguments, mcand and mlear. And you can see the operation that it does. It declares an initializes the variable product, and then makes use of a while loop. While this condition is true, this is what you do to the variables. Okay, this is what you do to product, this is what you do to mlear, and you continue this until the condition doesn't become false, and then you return the product. Okay, product is the output. You return this product to the main function. So we saw it was a simple conversion. Okay, you could expect to see simple conversions like this. Okay. So it says main function ends with done. So not bxlr. So there is no need to save this lr to the stack. So what it says, when do you need to save lr to the stack, or when do you need to save lr, is whenever you have a nested function call. That's when the return address gets lost, and that's when you need to save the value of lr to your stack. Now, let's say the main function, we are talking about the main function. The main function doesn't have to return the value to somewhere, right? Because no one calls the main function. The main function is always calling other functions. So the main function doesn't need to return something, return a result to any other function. That's why within the main function, you don't see something like a bxlr, because it doesn't have to return somewhere. Okay. And because it doesn't have to return somewhere, you don't need to save the lr to the stack for the main function. And all variables used in the main function are saved registers. Saved registers means the variable registers. So there is no need to save this onto the stack. When do you save saved registers to the stack? Whenever there is a chance that the callee function would garble up their values. So the main function is never a callee function, it's always a caller function. So there's no chance that, but there's no problem with the values being garbled up. Okay, because no one actually calls the main function. This could be a bit tricky if you don't understand. So do you have any questions regarding this argument? Volatile registers, temporary registers, save registers, they have different names, but some of that mean the same. Right? So the argument registers are called the volatile registers. They're also called the temporary registers. And saved registers are called the variable registers.
So I have a small confusion.
নেস্টেড প্রসিজারটা কি এক্সপ্লোর করা যায়?
Nested procedure?
নেস্টেড প্রসিজারটা কি একটু বাদ দেওয়া যায় সিলেবাস থেকে? মানে কনফিউজিং।
So nested procedure is part of the syllabus. It would be there. Which part is confusing regarding nested procedure? I think you just saw one example for nested procedure. This was the example. This is the example. We just saw one example. This is the one. Which part is confusing?
Yes, sir.
Sir, during the exam, should we follow the convention, like if it's specified in the question, or should we allowed to use any?
So it's always better to use the convention. Okay, so try to use the convention during the exam.
Oh, so it's better, but the mark will be allocated to it, sir?
So I'm not sure about that, but it's always good to use the standard convention and try to follow that. Okay.
Yeah, thank you, sir.
And regarding nested procedure, we just saw this one example in class. Okay, so it's a simple one where you had a sum square function and you are calling another function, which is the mult function from within. Okay, so what's the confusion here? What you need to take care of is the return address. The return address. Now, what's the return address? Or return address to what? Return address to the main function, because the main function would be calling this sum squared. Okay. So the sum square function needs to return its output to the main function, right? Because the main function is calling the sum square function. So the sum square function needs to return its output to the main function. But because you have this call to mult function, the return address is lost. Return address to the main function is lost. So that's why you save that return address to the stack before making the return. That's one thing you have to be aware of. Another thing you have to be aware of is what are the variables you need to store. So here you need to store this variable y, because you need this y later for the calculation. Once mult returns a result, this y needs to be added to that result to produce the output of the sum square function. So you want to store y because you need the value of y later. And y was stored in a volatile register. So anything in the volatile registers that you need later, you would want to store that to your stack. Okay, so that's about the volatile registers. How about the saved registers? Saved registers are the variable registers. So they are expressed in terms of V. And when do you need to store them? When, let's say, you are a callee function, and there's a chance that the callee function would change the values in those variable registers. Okay, so you don't want that. Why you don't want that? Because the main function would be using those variable register values. It would be looking for those old values. So if the callee function garbles up those values, then it's a problem for the main function. So that's why if there's a chance that the callee function would garble up those values in the variable registers, you would want to store the old values in the variable registers to the stack before them getting garbled up. Okay. Okay, this was the assembly conversion for the bottom part of this code. So basically we have two parts here, the main function and the subroutine. So we saw the code conversion for them. And from this example, what did you learn? So there are a few notes. It says no BL calls are made from mult. So if you see this mult function at the bottom, it doesn't call another function. So this is not an example of a nested procedure. Okay, so this is a simple function. It doesn't call another function. Okay, so here the return address won't be lost. So you don't need to store the return address to your stack. Right, so what it says is no BL calls are made. So no function calls are made from within the mult function. You don't use any save registers. So save registers are the V registers. If you see the code, you would see the code doesn't make use of any V registers, right? It only makes use of this A registers. It doesn't make use of the V registers. That's why you don't need to save them to the stack. Only temporary registers or the volatile argument registers are used for the intermediate calculations. You could have used save registers instead of the temporary registers. But if you did use save registers, you would have to save them to the stack. It says A2 is modified directly. So probably you don't need the value in A2. That's why it was modified directly instead of storing a copy of the old value. It was directly modified, so you don't need that value of A2. That's why it was done. And result was put in R0 before returning. So this is following the standard convention. So in conclusion, this is the summary, that functions are called using BL and return using BXLR. Stack is your friend. Use it to save anything you need. Just be sure to leave it the way you found it. Right? So what it means, you create space in the stack by decrementing your pointer, stack pointer. But after you're done using the stack, you have to restore the stack before leaving the function or before returning to the main function. Okay, you be sure to leave it the way you found it by now incrementing the stack at the end. First, you decrement the stack in order to create space in the stack. Once you are done using the stack, you now increment the stack. So you now point to the original location before returning. Any questions regarding this? Stack recursion, we saw the data structure. It follows a LIFO structure, last in, first out. Whatever data Can you hear me, everyone?
Yes, sir.
Okay, so from here, you just have to learn the motivation, okay, behind using push-pull. Why do we go for push-pull and why we don't go for open drain? Okay. Why do we always choose push-pull as the output type? What's the problem with open drain? What exactly is the problem with the open drain? So this slide tells you what's the problem with open drain. Okay. you can see whenever this output bit is 1, what happens? The controller inverts it to 0, and 0 enters the gate terminal of the MOSFET. This is an NMOS, so that's why your MOSFET turns off. Whenever it's off, you replace that using an open switch. Now you see, whenever you have an open switch here, it causes this output to float. Okay, so the output, whenever this output bit is 1, the GPIO pin has a high impedance to the external circuit because of this open NMOS. Right, so you want the output at the output pin to be 1, but it has a high impedance value. Right, so this is not something you want, right? So that's why we never use open drain as the output type. We always go for push-pull. Generally we always go for push-pull. Okay, so for this kind of a scenario, push-pull is applicable or preferred. Right, you can see that this pin offers a high impedance to the external circuit whenever the output bit has a value of 1. Okay. That's basically the motivation of using push-pull instead of open drain. And finally, we talked about the slew rate, where there can be different speeds at which the signals transition. Right? What's the problem with the high GPIO speed? How to configure the speed, right? Which speed to use. So it depends on the application, right? So if you're toggling LEDs, you would like a low speed. If you're using a low speed peripheral or slow peripheral, you would want a high speed for the transitions. Okay, so you have to configure or decide the speed based on the peripheral speed. So we saw what was slew rate, right? And so here again, it repeats the difference between push-pull and open drain, right? So you can see when the output bit is 1, push-pull gives you a 1. When the output bit is low, push-pull gives you a low. So this high and low are at the pins, okay? At the pins. So when the values are valid internally, the values are also valid at the pins externally. Okay, but that thing doesn't happen with open drain. Open drain, you can see that whenever output bit is 1, at the pin you get a high impedance value because the MOSFET was open. You replace that using an open switch that offers a high impedance value, high impedance to the external circuit. Okay, that's why we don't go for open drain. Internals of ODR, we already talked about ODR, how it can be used to control the value at a particular pin. So for the exam, you would want to revise this code. Okay. How you can turn up the LED, what are the steps, right? And the expressions that are used. So here, what's important? The steps. What do you have to do one by one? Okay. Enabling the clock, setting the mode, setting the output type, and then finally setting the output value.
Sir, for the dual, does it mean we have to end the 3,
For which line?
the second line?
Yes, second line. You have to end with not 3. Okay, not 3 means not 1 1, which is actually equal to 0 0. Is that clear?
So basically bitwise of 4 with 0 0.
Bitwise and with 0 0. No, bitwise and with the data in bits 4 and 5. So remember, the mode R register has 2 bits for 1 pin.
Yeah.
So because you have a 4 here, it's referring to bits 5 and 4. If you look at the internal structure again, that would be clear. That things would become clear. Okay, whenever you're saying 4, you're actually referring to the data in bits 4 and 5. So whatever data you have in bits 4 and 5, you add that data with 0 0.
All right, now it's clear. Thank you, sir.
Okay, so yeah, so this lines basically tell you which are the registers you need, which port you need, which clock you need. Okay, this tells you that you need the mode R register. You cleared the bit first, and then you set a bit to 1 in order to convert to the output mode. Then you set the output type. Then you set the value in the ODR register, either to a high or to a low. Because in this case, you want to light up the LED, you want your output to be 1, right? A high. So that's like some finite amount of voltages that would allow a current to flow through the register and light up your, a current to flow through LED and light up your LED. Okay? That's why you want the output to be 1. Any questions regarding this? Internal structure. So for input, which are the relevant registers? For output, which are the relevant registers? Is the Schmidt trigger part of the input or the output? What are all the possible modes? Right? What are the possible output types? What can you do with the PUPDR register? Why do you sometimes use? When do you use this option? No pull up, pull down. Okay. When do you use this option? No pull up, pull down. It's when you have your pin externally pulled up or pulled down, so that then you don't need a pull up or a pull down internally. Okay, that's when you use this 0 state. Okay, no pull up, pull down. And if you don't have a pull up or a pull down externally, you would want to have a pull up and a pull down, or a pull down internally. Okay, why do you need this pull ups, pull downs? Is to avoid any high impedance value internally. Okay, so for whenever you're talking about the output, which are the registers that play a role? The mode register plays a role, the output type register plays a role, the output data register plays a role, and the PUPDR register plays a role. Whenever you're talking about the input, which registers play a role? The input data register plays a role, the PUPDR register plays a role. Okay, and the Schmidt trigger is actually part of the input network. What was functionality we discussed? That it reduces noise, it improves the slew rate. Okay, and how is noise inserted or incorporated into the system? Why is the slew rate slow? What kind of an output does a comparator produce from this input signal, from a given input signal and threshold? How is the output produced? And how is the Schmidt trigger different from a comparator? In that, because you can see the comparator only compares with one threshold level, whereas the Schmidt trigger compares with 2 different threshold levels, threshold high and threshold low, which forms an immunity band. Right? So you can see that the Schmidt trigger output is different from the comparator output. Right? And any fluctuations within the immunity band is ignored for a Schmidt trigger. Internals of the peripheral enable clock register. Right? How do you enable the clock for any port? You define a macro like this. RCC is actually representing your reset and control clock module. And then this is the name of the register that has the clock information for the peripheral clock. This is the register that you use to enable a particular clock. So I think this is what we discussed last class. So it was like pretty recent. Anyone has any questions from slides 15 to 31? This is what we discussed last class. I mean, the keypad scan is kind of simple, right? The keypad scan is kind of simple. But before that, any questions regarding this joystick configuration? So you'd want to look at this piece of code for the joystick.
What can I expect from here?
So the steps that are involved. Also, if you are given a configuration, how you would read the input from a pin. Okay, so here, what was the configuration? Your center button was connected to this pin, right? And your center button was connected to this pin. So if you wanted to read the input, I mean, whether the center button was pressed or not, if you want to detect that, you need a piece of code, right? Similarly, for all the buttons, if that was pressed or not, if you want to detect that, you need a piece of code. So this is the code to determine whether the center button was pressed or not. Okay, so if I give you a similar device like a joystick and I say this button is connected to this pin, how would you read the input at that button, whether it was pressed or not. Something like that, okay? I might change the name of this button, change the name of this pin, but basically ask the same question. I mean, that's a possibility. I'm not saying it will come up, but this is the type of questions you might see. Or just what are the relevant registers involved? You might ask what are the relevant registers involved. Here, what are the relevant registers? Your clock enable register is a relevant register. So it's a HB2 peripheral clock enable register. So that's a relevant register. The mode register, the PUPDR, right? The IDR. IDR is called the input data register. Since here you're detecting an input, IDR register comes into the picture, the input data register. So what are the registers involved? Okay, that could be a possible question. I could give you a piece of code and tell you what a particular line, ask you what a particular line is doing, right? And why do you need that line, or what is a particular thing representing a value. So it's important that you have the concept layer. Okay.
So basically, we should know how to write the code and what the code does.
Yeah, correct. So how you read the input from a pin, okay? Because a pin is actually connected to a button, right? So whether the button was pressed or not, you get an idea from the value in the pin. Okay. For this case, how did you know if the button was pressed? You actually read pin 0. You read the value from pin 0. How do you read? Using this line. Okay. You're reading the value in pin 0, and from that value you can actually determine whether the button was pressed or not. And these 3 slides basically show you the internals of the relevant registers relevant to the input, right? Whenever you're using the pin as an input pin, what are the relevant registers? The clock enable register, the PUPDR, and IDR. So of course you would need IDR, because IDR actually contains the input values. It contains the values of the signals that enter the input pin. Okay, so that's important. IDR, PUPDR, and clock enable register. You would want to see the internals and how they function basically. So anyone has a question regarding this clock enable register, or the pull up pull down register, or the IDR?
No, sir.
Is it clear what these 3 registers do? I mean, we discussed this last class, right? So today's Monday. So yesterday, yeah. So we had a discussion on this yesterday. So it's pretty recent. So I'm not delving into the details because. Right. So just giving you a hint of what could come up from which chapter. Right. So we discussed this module 10. From module 5, what could come up? Instruction to machine code conversion. Okay, as simple as that. Instruction to machine code conversion. And for the data transfer instructions, for like load and store instructions, you might be given something like a memory map with all those rows, different memory locations. I might ask you to fill that up, or it could be partially filled up. And I might ask you something about the data that is there. Okay, and right, for so we kind of had a discussion on everything that's there in the syllabus. So any final questions, or any topic, any concept that you didn't understand, that's not clear? Anyone? If not, let's move to the attendance for today.